Good evening, everybody. Welcome to our last Great Lakes lectures of the series until the fall. We'll be back in the fall with more lectures. And we have a great speaker joining us for our last talk. We have Dr. Abby Stevens here with us. Abby is an NSF postdoctoral fellow at the University of Michigan and MSU. Her research involves looking at black holes and neutron stars using X-rays, which we'll be hearing a lot more about today. Abby is also involved in a plethora of other activities, including using the space telescopes, the X-ray space telescopes. She's also involved in open source coding. She does outreach activities for science and also consulting. She's involved in mental health awareness and well-being activities in academia, and also she's been with us here for a while at MSU. Before coming to MSU, she obtained her PhD at the University of Amsterdam in the Netherlands. Before that, she got her MSc in the University of Alberta in Canada, and even more before that, she got her BA at Bard College in upstate New York. So we're very lucky to have Abby here with us today. Thank you very much for joining us, and we're looking forward to your talk.
Wonderful. Thank you so much.
I'll pass over to you.
And where's the clicky?
Yeah.
Okay.
Okay, you can take your mask off.
Yep. Oh my goodness. Hello, everybody. I am alone in the room and fully vaccinated, and we agreed on this beforehand. So, as Dan said, my name is Abby Stevens, and I'm going to be telling you about black holes, what they are and how we can see them. And the slides are working. So black holes are what happen when you have a whole lot of stuff or mass in a very, very small space. So what's important for black holes, it's not just the mass that they have, but it's also having it be really, really compact. So it's like really, really, really tightly in there. A lot of the ways that we kind of imagine black holes as scientists is thinking of them in three-dimensional space can be kind of hard to wrap our head around. So instead, we think of space and time as being like a two-dimensional fabric. This kind of helps us ease our thinking of it. So if we think of something having mass, it will bend that fabric, and how things move on that fabric is like how they behave in gravity. So our sun has a gravitational field. It's got mass, and so it bends this space-time thing a little bit. So if something like the Earth is in orbit around the sun, it will move in a circle. Pardon me, this is my first time using a weatherman-like camera setup. It will kind of move in a circle around the sun there on like the fabric of space-time, as we call it. But black holes have so much mass in such a small space that they have very, very powerful gravity. And so the amount of gravity, like the strength of their gravitational field, we can think of it as like the slope on this fabric of space-time here. So we see that for black holes, even though they might have the same mass as the sun, they have it's so much more compact that their gravity is much stronger, and so it gets super, super deep. The thing that makes black holes black is that they have what we call an escape velocity faster than the speed of light. So everything with mass and with a gravitational field has an escape velocity. On Earth, for example, airplanes do not go faster than the escape velocity of Earth, so airplanes will always come back down to the ground. Rocket ships, however, these do go faster than the escape velocity, so they can escape the gravitational field of the Earth and go to like the moon or Mars or an asteroid. But for black holes, their escape velocity, the speed you would have to go to get away from them, is so fast, it's faster than the speed of light. But nothing can go faster than the speed of light. This is a rule of physics. So nothing can escape from them, not even light itself. This makes them look dark or black to us. So if we think of kind of the parts of a black hole, this is a computer simulation of one. The parts that people are most familiar with are the event horizon, which is this bit right in there. Event horizon and the singularity, which is what's at the center of it. So the event horizon is like the point of no return. It's once you pass through this event horizon that nothing, not even light, can escape from it. Outside of the event horizon, it is possible to escape in general. The singularity is more of a mathematical concept than a physical concept, and a lot of what we know about black holes is actually from the math of how black holes work. We have not sent any probes or any spaceships to a black hole. They're too far away for us to do that. So everything we know about them is what we've seen and what we can do the math about them for. It also has this thing called a photon sphere. And so this is because black holes can also bend the path of light, which we'll talk more about at the end of the talk. And so the light that's being shined from stuff really close by, it forms this kind of like a little light shield all the way around it, which is this thin little thing right there. It also has, we call this an accretion disk, don't worry about it, all of this stuff that's around near the black hole, and this stuff is shining a lot of light. Not pictured in this thing, but we also have, there we go. We also have relativistic jets. These are powered by the magnetic field of the stuff around the black hole, and these ones can get really, really big. They can go much, much bigger than the black hole and all the stuff around it, and these can shine really brightly, and we can see them too. And so one thing I wanted to point out is that the danger zone for a black hole is very, very small. So most stuff around black holes is totally fine. It's not going to fall in, and it can orbit stably around the black hole kind of forever. The way that the moon can orbit stably around the Earth and the Earth orbits stably around the sun, a lot of stuff can just orbit stably around a black hole, and it's totally fine. One fun fact is that if you were to somehow magically replace the sun in our solar system with a black hole of the exact same mass, its gravitational field out at our distance would be the same, and the Earth would keep orbiting around it totally fine as though nothing had changed. Because its mass is the same, and it's so far away that the gravitational field is the same, so you'd have to be, even Mercury would be totally fine. You'd have to be well within the current radius of the sun to get stuck in the danger zone of that black hole, if that were to happen. But it's not going to happen. Now let's talk a little bit more about types of black holes. So there are two main types of black holes. You have small black holes. These are formed from the death and collapse of a big star. So we call them stellar or stellar mass black holes. These ones are 10 to 100 times the mass of our sun, roughly. Then we have really, really big black holes. These ones have been around since very early in the universe, and these are at the centers of galaxies. So we call them supermassive black holes. These ones tend to be millions to billions of times the mass of the sun. You'll notice I say the mass of the sun, so all the stuff that's in the sun. We use that as a unit of measurement for mass because things in astronomy get really big. So using something like pounds or kilograms doesn't really make much sense when we're talking about things that are this massive. And I want to take a brief interlude to talk about just the scale of the numbers from the small black holes to the big black holes. So it sounds trivial to say this. I'm going to go on this side. It sounds trivial to say this, but the universe is really, really big, and therefore the numbers that we use to describe how big it get really, really big. And we use these numbers a lot when kind of discussing things even the economy or the size of the universe or how far away things are. But I want us to kind of intuit a little bit just what the scale of these numbers is. So let's think about them in terms of seconds. We all know what 1 second is, roughly this. And so 1,000 seconds is 16 minutes. And that makes sense. We know what 16 minutes is. We can wrap our heads around that. If we then want to talk about what 1 million is compared to 1,000, well, 1 million seconds is 11 days, a week and a half. So, okay, it's a big jump to go from 16 minutes to 11 days, but that's the jump from 1,000 to 1 million. But we can still grasp what that is, right? If we then talk about 1 billion seconds, this is 32 years, roughly. So to put this in perspective, I am not quite yet 1 billion seconds old. So by going from million to billion in the scale of numbers, we've gone from a week and a half to my entire lifetime. And that's the scale of numbers that we're talking about when we're talking about how big black holes can get. Black holes can be as big as the equivalent of 32 years worth of big, if you want to think of it that way. So some things can be really, really small, like the small black holes are 10 to 100 times the mass of the sun. The really, really big black holes are millions to billions of times the mass of the sun. So keep that in mind while we talk about the rest of the numbers in here. So the smallest black hole we've ever seen is about 3 times the mass of our sun, and this is as small as a black hole can be. If it were any smaller, it wouldn't be a black hole. It would be something we call a neutron star, which I also think is really cool, and we can talk about that later if you want. The biggest black hole we've ever seen is about 60 billion times the mass of our sun, and there's no limit on how big black holes can get. They can keep on getting bigger if they keep eating, and there probably is a bigger black hole out there, we just haven't seen it yet. So this is pretty exciting if you like black holes and want them to take over. But how do we study them? How do we know how big these black holes are? How do we know like what they're doing? Because we can't just grab one, put it on a table, shine a light on it, and study it. Instead, to see one, we have to wait for it to send light or something in our direction. So we can see black holes by the effects they have on their space environments. And I'm going to talk through 5 of the ways we have to do that to learn more about these black holes. So the first way we have is to take a picture of black holes using radio light. This is a new way we have of seeing black holes. This was first done in about 2016, in 2018. And this was done of a supermassive black hole that is near to our own. This one is called M87 Star. And the group that did this, I think the credit is cut off at the bottom. This is from the Event Horizon telescopes. You can look up more about them later. So you may have seen this lumpy orange donut in the news a few years ago. To me, this was the most exciting lumpy orange donut I have ever seen, because this is actually light coming from stuff just outside of the black hole right before that stuff is going to fall into the black hole. So this is super, super exciting. The black part in the center, that's not just the event horizon, that's also this like shadow area of like just a little bit bigger than the event horizon. So the event horizon is in there, and there's a bit more space, and then we have all of this stuff that's right around the outside. So the light that's being shined from this stuff here, it's getting like excited and spun up around these magnetic field lines, and then it's kind of careening through the universe and coming to us here on Earth. It goes out in all directions in general, and we see the stuff that comes to the Earth. If we were to do computer simulations, this is how we often check if our understanding is correct. So if we could have higher resolution images, we can see what it might look like. So here we are blurring it a bit to show that it indeed compares to what we took the picture of. I say we, I didn't do this. And if we were to have a higher resolution image, if we could have like almost unlimited resolution, it would actually look like this very skinny thing here, which is pretty cool. And when we're talking about the resolution of how we get this for the telescopes, we're using radio light, and these require really, really big antennae to see radio waves from stuff in space. So we have like individual radio telescopes here that we combine together with computers on the back end to treat them like it's one large telescope. This is called the Very Large Array, or the VLA. Don't let astronomers name things in general. And they can use all of these telescopes together as though it's one very big telescope to look for radio stuff from space. However, this black hole, this event horizon that it's trying to image in the shadow, is really, really, really small. It is like trying to image, if you were standing in New York, if you were trying to read the date on a quarter in Los Angeles. This is extremely far, and it's super tiny. I mean, if you were to hold a quarter on the other side of this room, I couldn't see what the date is on it. But they were trying to use radio telescopes to take an image of something that small. So they couldn't just use one set of telescopes set up like this. Instead, they had to combine most of the radio telescopes that we have on Earth. And that way they could make an Earth-sized radio telescope detector. So they were combining telescopes on the South Pole, and in Hawaii, and in South America, North America, and Europe. And by combining all of these together with a lot of complicated computer stuff, they're able to take the image that we saw. And when they're doing this, here we go. This is showing how the more antennae you have, the clearer your picture gets. So the farther apart they are, the smaller you can see, and then the more antennae you have, the better resolution, or like the clearer the picture gets. And so not only does it help to have these radio telescopes to take a picture of a black hole across the Earth, but the Earth rotates. And so as the Earth rotates, the position of each of those radio telescopes moves a little bit in relation to the black hole. And so it's kind of like it's kind of like you have even more radio telescopes if you average over a few hours or a day or something. So this is a really cool technique that we were finally able to use to take a picture of a supermassive black hole using radio light. And most recently, they added some lines to the image. This came out in, I think, March of this year, of 2021. And these lines are showing the polarization of this light, of stuff from right outside the black hole. Polarization is related to the magnetic field of this stuff, so these aren't quite magnetic field lines, but this polarization is the same kind of thing that your polarized sunglasses can block. Light has polarization. So this was really exciting as well, to show that we can learn a little bit about the magnetic field structure of this material close to the black hole. Moving on to another way we have to see black holes. Another way is when they're eating their star friends. And this is the kind that I actually study in my own research. So a lot of times we'll have a small stellar mass black hole, and they kind of grow up with a normal star like our sun, and they orbit around each other, just like how the Earth and the Moon orbit around each other. And they hang out together for millions of years. And oftentimes they're pretty close together. And so some of the outer stuff from the star friend is actually more gravitationally attracted to the black hole than it is to its own star. So this stuff starts to fall down towards the black hole because of the gravity of the black hole. And as it falls down towards the black hole kind of collects it in almost like a plate as it's getting ready to eat it. We call this an accretion disk. And as it's collecting this food from the star in its plate, it's getting super, super, super hot for plasma physics reasons. And it gets so hot, it's about 20 million degrees Fahrenheit, which is 100 times hotter than the surface of the sun. And so the heat light that it shines from this is really, really high energy X-rays. And this is really exciting because we can then use X-ray telescopes to look for this kind of heat light from the stuff that the black hole is eating from its star friend. Black holes are bad friends. Don't be friends with them. Here's a video that will hopefully play, of a computer simulation of what this might look like. So as the star gets close enough to the black hole, it starts to rip it apart, starts to pull a bit off of it and then rip it apart. And then the stuff kind of fills out all around the black hole, but it's quite messy. There's stuff blowing away. It's kind of like a Cookie Monster thing. We've got this jet coming out the top and bottom. But so keep in mind here that the black hole is always there in this video, but you can only see it when it's eating the other star. Comes around, and then as it's doing this, it's getting super, super hot, and we can see that, which is very exciting. Sometimes this happens really quickly over months, and we call it a tidal disruption event because it tidally rips the star apart. And sometimes this happens just very, very slowly over millions of years, and we call these X-ray binaries. And actually the first black hole that we ever saw, it's called Cygnus X1, and we saw the X-rays coming from it in 1972. This was how we saw our first black hole. And if you think about it, 1972 is not actually that long ago, so this is quite a recent and exciting field of research. So when we want to look at this X-ray light coming from the black hole eating its star friend, we have to use some interesting techniques to be able to actually see it. Because the colors that we can actually see are a very, very small part of all of the light that exists. The science term for this is the electromagnetic spectrum. And so all kinds of waves are all actually connected. They're just different types of energies of the same type of thing. So we've got radio waves on the bottom, we've got microwaves here. So the thing in your kitchen is a microwave oven because it uses microwaves to heat stuff up. Infrared is heat, human bodies shine their heat light in infrared. Visible is what we can see. That's how you're seeing me and I'm seeing all of this stuff. Our sun shines a lot of visible light. Ultraviolet, UV, this is what gives you skin cancer and sunburns. And then X-ray light. X-ray light is very energetic. This is what they use to take pictures of your bones and stuff. And then gamma ray is the most energetic. This comes from radioactive stuff and nuclear stuff. So the actual light that we can see is a very small part of all the kinds of light that exist. And so X-rays from space can't get through Earth's atmosphere, which is really great for us on Earth, but it's kind of sad for X-ray astronomers like myself. So we have to put our X-ray telescopes on satellites and launch them into space on rocket ships. That way we can see X-rays from stuff in space. One of the X-ray telescopes that I use is called Nustar, and it is this box swiveling around. It is attached to the International Space Station, and this is a video from, I think, 2018 or so. We've got the solar panels of the space station in the background there. Nustar is about 1 meter cubed, so it's like the size of a dishwasher, roughly. And it's an X-ray telescope. It does not look at all like the radio telescopes we saw before. It doesn't look at all like the maybe visible telescopes that you have seen at like an observatory or something. The X-rays come through the circles that are on the top part right now. That part. There we go, that part. The X-rays come in through those circles, and X-rays are really, really, really high energy light. So we have to be able to like focus them just a little bit, just like bounce them just a little bit. So the X-rays come in through those circles, and then on the back plane of the box are the computer detector chips that read out the X-rays. So this looks very different because X-rays are a different energy of light than visible or radio. Another X-ray telescope that I use is called Nustar. For this one, it looks a little bit different again because it's looking at a different energy of X-rays than what Nustar looks at. So for this one, the X-rays come in through this, there we go, this front part here. The X-rays come in through here, and then we have about 30 feet of free space. We have this structure here to keep the telescope together. We have about 30 feet or 10 meters for the X-rays to then be focused down onto the detectors, which is in the back thing over there. So I use telescopes like Nustar and Nustar to look at this black holes eating their star friends, shredding them up, and then having this like plate of hot star stuff that's getting super, super hot. We can see the X-rays from those with these telescopes. Another way we have to see black holes, this is kind of related, so it's like a 2B. Sometimes we have supermassive black holes that are also eating stuff, and they're not eating quite individual stars, but just like big clouds of dust and gas that happen to be in the galaxy. Scientists call these active galactic nuclei and quasars, depending on how far away and how big they are. So what I'm showing here, this is a Chandra deep field. So this is a picture taken with the Chandra Space Telescope in the X-rays. And what they did is they stared at what looked like a blank part of sky for a very, very long time. And each of these individual dots kind of looks like stars, but actually all of them, basically all of them, are individual galaxies that are just super, super far away. And these galaxies are shining up in X-rays because they are also eating a bit of gas. So what I'm going to play now, and I hope you can hear it on the microphone, is astrosonification of this data set. So the color that you see is related to the pitch of it. And if you listen to this on your home speakers, the stereo of the sound tells you which side of the picture it's on. Astrosonification is so cool. So what we were listening to is the color of X-ray light, so the heat of the gas that it's eating up, basically, in X-rays. Oh, there we go. Another way we have to see black holes, specifically supermassive black holes, is by seeing how they impact nearby orbiting stars. So this is a picture of the center of our own Milky Way galaxy, and each of these rainbow dots, you can kind of only see the blue in the screen. Each of these rainbow dots is an individual star. So we've taken very high resolution pictures of the center of our galaxy. And this white star here, sorry, I'm bad with this. The white star there there's nothing there in the picture, but that is showing where the supermassive black hole is. So if there were no black hole, if it were just nothing at all there, then when I press play, we should see all of these stars just move in a straight line until they collide with one another. However, since there's a supermassive black hole with a really strong gravitational field, it instead causes these stars to orbit around it. So the year is going to count down up in the top here when I press play, and we can see how the stars orbit. So you see one of them just like slingshotted around. The yellow one went for almost a full loop there. Pink's going for a circle. The yellow one's coming back around. We're up to 2015 now. Yellow did another loop. And now 2020. And then they're showcasing this particular star. They named it SO2. Again, don't let astronomers name stuff. And we see that it does a full loop. These images that were taken over, 15 years, or no, 25, oh no, over 25 years, these show conclusively that there has to be a supermassive black hole at the center of our galaxy. And so this kind of research is what led to the Nobel Prize in Physics in 2020 to two professors who were doing the observational data and another professor who did a lot of the computations and the theory beforehand. This one is called Sagittarius A star. This is the supermassive black hole at the center of our Milky Way galaxy. It's about 4.3 million times the mass of the sun, which it turns out is like a pretty nice normal mass for a supermassive black hole in like a pretty standard galaxy. So this is great. Another way we have to see black holes is not using any kind of light whatsoever, but it's using gravitational waves to see them when they smash together. So in this video I'm going to play, this is a computer simulation, and we're going to see just as two black holes are spinning closer and closer together, and then they finally smash together at the end. The yellow and the blue is just showing like the gravitational waves, and then at the bottom here we have this waveform, which is what the gravitational wave would look like if we saw it on Earth. So we see they spin up, get closer and closer, the waves get bigger and faster, smash together, and then it's like ripples in a pond. It's going to go again. So they're orbiting around each other, but they're getting closer and closer. And the closer they get, the faster they spin, and the gravitational waves get bigger and faster. And at the very end, they smash together, shining out one final burst of gravitational waves, and then we have one black hole left over at the end. So again, there's no light coming from any of this at all. It's just gravitational waves that we see. So when we're looking for these gravitational waves, we have to use a new kind of detector because telescopes aren't going to cut it. So this is what LIGO and Virgo do. They send laser beams down these super, super long arms, and they want to see how the laser beams come back together. So we're following like a particular light wave right now. It reflects off a mirror at the end of these giant arms. And then when the two beams come back together, they're supposed to come back in like a certain pattern. But if a gravitational wave passes through the Earth and passes through the detector at that time, it very slightly changes the length of each of those arms. And so it changes how the waves add up or subtract at the very end here. And how they add up or subtract makes it look bright or dark, which gives us the wave that we actually see. So gravitational waves like this have always been passing through the Earth, but we only had the technology to really see them for the first time in 2015. But it was very, very exciting. So the first black hole smashing together that we saw, we have these waveforms over here. This is actual science data. There were two different detectors with LIGO, one in Washington State and one in Mississippi. And they each saw it a little bit offset because there's space between them. And so as the wave passes through the Earth, it first hits one and then it hits the other. And then we can see that they add up together. If you shift the other one by time, we see that they are indeed like the same thing, which is super exciting. And we were able to use theories for things that were developed by Einstein to predict what it should look like. And we see that the prediction, which is like the smooth lines over here, the prediction lines up really, really well with what we actually measured. So it shows that Einstein was right, yet again. Pretty exciting. One of the ways that we can show this data is, again, using sound. The frequency that these black holes were spinning together, and as they finally smashed together, that frequency is actually audible to people. So we produced what we call a black hole chirp. And so you'll hear it twice on its own, and then they've moved it up to a frequency range better for people to hear also. So this will play through twice. So we have the time of the in-spiral, the final in-spiral, and then when they smash together, that time's going to come here, and you'll see kind of the waves as it goes. So with the first lower bit, that was kind of hard to hear because it's just at the bottom of our hearing range. But when they move it up to a higher frequency range that we can actually hear pretty well, you can hear it almost sounds like a water droplet dropping into a pond. That's the sound of two black holes smashing together, which is super, super exciting. So again, there's no light coming from anywhere in this. Instead, it's just these gravitational waves that we can see. So we've seen a whole bunch of black holes smashing together at this point. This is an example of some of them. And so what we've done is we're going to show how the different sizes of the black holes and their distances affects what those waves look like. That wave that we actually see, that's the only thing we see in this whole scenario. So this is going to show you how the different masses and distances of the black holes affects how the wave looks. So everything's going to spin down together at the same time, and I want you to keep an eye on like how the different waves look and how the different black holes are. So for example, oh, please go. No. No. It's not going to go. Okay. So for these two black holes, these two are quite big, and so they have a really, really big wave, whereas these ones over here, these ones are quite small, so they have a very small little fast wave as they spin down together. Sorry that didn't work. You can find it on YouTube. I'll tweet the link at the end. The final way, oh, wait, oh, it's going. Oh my goodness. I talked for too long and now it froze. Never mind, sorry about that. The final way we have to see black holes is when they are bending light from stuff behind them. So black holes can not only bend the path of stars nearby to have the stars orbit around them, and not only can their gravity like make them come together and smash and merge together, but this gravity can actually bend light from stuff behind them. So here we have a picture of a galaxy, a real picture of a galaxy, and then we've artificially put a black hole and had it like move across the image to show you what it would look like if there were a black hole in the way at different points. So if you were to take a picture of a galaxy and it looks like that, or something, you say that is not what galaxies are supposed to look like. Then you can figure out that, oh, there's probably something like a black hole in the way that's causing the light to bend and look funny. So if you know what your galaxy does look like and you know what it's supposed to look like, you can compare them to actually see like how big the black hole is and how far it is in between. Looks pretty cool. So here's a little science diagram showing it. If we got the Earth here, where's my hand? The Earth is here. So if you've got some black hole and also the rest of its galaxy, because these tend to be supermassive black holes, some black hole in the way, and then we've got a distant galaxy that we're taking a picture of, the gravity of the black hole that's in the way bends the light around it. So when we are looking from Earth, we see the black hole and galaxy that's in the middle here, but we also can see these two images on the top and bottom because it kind of projects a little bit. And then this can also help us figure out the distance to the black hole and the host galaxy, so that the thing that's causing the light to bend, and then the thing in the background that we're actually taking a picture of. So I'll show some real examples of that. This is a picture taken with the Hubble Space Telescope, and this is an example of what we call an Einstein Ring, because the black hole and galaxy at the center here bend the light from the galaxy in the background so that it forms almost an entire ring. So at first, if you look at this, you could say, well, that looks kind of like a star, perhaps. But we know that stars don't have strong enough gravity to bend light from a whole galaxy in exactly this way. So we know that it has to be a black hole there as well. There's another thing called an Einstein cross, which is where it looks kind of like a clover leaf. So we have 4 images. Here we go. There we go. We've got 4 images, and then the thing in the middle that's doing the lensing. We can see that also, Einstein cross. So the thing is actually just behind it, just the way that the light projects because of the lensing causes it to look like a cross or like a ring. So the strong gravity of the black hole here is acting like a lens, bending and distorting the image. And this leads us to what I call the creepiest image in all of astronomy. This little smiley face. This is caused by gravitational lensing. We have 2 black holes as the eyes here. These are supermassive black holes that also have like a whole galaxy and stuff associated with them. and it causes this creepy little smile and with these little side ear things of distant galaxies that are even further behind them. Pretty creepy stuff. Thanks to gravitational lensing, thanks to black holes. So that brings us to the end of my talk. So the ways we have of seeing black holes are taking a picture using radio light. We can see them in X-rays when they're eating their star friend or eating other gas. We can see the effects they have on nearby orbiting stars. We can see them through gravitational waves when they smash together. And we can also see when they bend light from stuff behind them. Pretty cool. So even though we can't see black holes directly, we can still see the effects they have on stuff around them. Thank you very much.
Okay, thank you very much, Abby. We've got some questions which I'll read out, and if you can just summarize.
Okay, so Dan is going to read out some questions from the Facebook, and I'm going to summarize and then answer them.
Okay, so John asks, was the technology used to see the smallest black hole the same as the technology used to see the largest black hole?
Ooh, no. So John asks if the technology used to see the smallest black hole is the same as the technology that was used to see the biggest black hole. So no, we have a bunch of different ways of detecting how massive the black holes are. I don't recall off the top of my head what method was used to see the smallest black hole, but this black hole is called the unicorn because it's in the Monoceros constellation, galaxy cluster thing. So if you look up the unicorn black hole, you can read all about that. I'm pretty sure that was seen because of dynamics with a star that's right nearby. So we could see how a star is being pulled and then figure out how massive this secret black hole has to be instead. Whereas with the most massive black hole, the one that's 60 billion times the mass of the sun, this one is super, super far away, just incredibly far away, and it's eating a bunch of gas, and this gas is shining out atomic lines, and we can measure the atomic lines where they are and know where they're supposed to be and figure out how massive the black hole at the center must be that way. So we have a bunch of different techniques of figuring out how massive black holes are.
Okay, thank you. Emmy asks, people talk about asteroids hitting the Earth, but are we in any danger of a black hole hitting the Earth, and would we be able to survive it?
So the question is, people talk about asteroids hitting the Earth. Is there any danger of a black hole hitting the Earth? Will we survive it? So first of all, no, there is no danger of a black hole hitting the Earth. They are very far away. The closest one to us is still 1,500 light years away or so, which is very far. So there's no black holes that are close to us. They're not going to come anywhere for us. So don't worry about black holes personally. They're just a cool thing to think about. They're not anything that we have to worry about. If one were to come into the solar system, so if we were to just kind of remove ourselves from reality for a second and just think about some fun math stuff, if you were to have the sun and magically replace it with a black hole of the exact same mass, the Earth is outside the danger zone, so nothing would happen to the Earth. It wouldn't fall into the black hole. It would keep on orbiting as though the sun were also still there. It would be totally fine. The thing that would hurt us in the end is the lack of light from the sun. But it being a black hole is not the problem. We are outside the danger zone, and there is no worry. So the actual danger zone of getting stuck forever in the black hole is super, super small.
Okay, Maureen asks, there's kind of two questions together here. Maureen asks, did Einstein predict black holes, and do black holes die like stars do?
Okay, so they asked, did Einstein predict black holes, and do black holes die like stars do? So I am trying to remember my science history. I don't recall if Einstein predicted black holes. I know that Fritz Zwicky is the first one who came up with the term for a black hole. I think Einstein came along a little bit after the idea of black holes came about. Dan and Elias are nodding, so I'm going to go along with that. Sorry, I don't have those exact dates on the top of my head. But once we had the idea of black holes, Einstein worked out how the gravity would work around them really well. What was the second part of the question?
Do black holes die like stars?
Do black holes die like stars do? Great question. So a black hole is born when a massive star dies, and black holes do not die the way stars do. So for a star, we talk about a star being born when nuclear burning ignites at the center of it. We have this big cluster of gas that's all falling together and clumping together, and when it's big enough and hot enough and dense enough that nuclear burning ignites, that's when the star is born. And the star is alive for as long as it's doing nuclear burning at the center. So our sun is doing that right now. That's how it produces light and heat. And then eventually the star runs out of fuel, and it stops doing its nuclear burning because there's nothing left to burn, and then that's when we call the star dies. So if it's a massive star, then it goes supernova, and we can make a black hole. However, black holes don't have anything like that that's causing them to be alive in the sense. So black holes keep on going kind of forever, which if you like black holes is kind of exciting. So they can kind of keep eating stuff. If nothing comes nearby, like if nothing gets close enough to them, then they don't eat and they just kind of hang out and like don't really do anything. But if stuff is falling into the black hole and they're eating stuff, they can get bigger. One of the big questions that we have is, do the small stellar mass black holes end up becoming the bigger, like supermassive black holes? Because in science right now, we know that these small stellar mass black holes, which again are like 10 to 100 times the mass of the sun, we've seen like millions of these, we expect there to be millions of these in our galaxy and also in all the other galaxies. And then for the supermassive black holes, these are at the centers of kind of all of the galaxies, and so there's like billions of these. However, we only have seen like maybe 2 intermediate black holes that are like 1,000 to 10,000 times the mass of the sun. So this would be like if you saw an alien population, you saw millions of kids, billions of grown-ups, and 2 teenagers. You wouldn't necessarily think that the kids grow up to become teenagers to become the adults. You might think that the kids and the adults are just like formed differently. So we've only seen 2 teenage black holes, and that's a maybe. I have a poll going on my Twitter right now asking astronomers how many of the claims they believe. So you can check my Twitter if you want to know more. So we're not entirely sure if the small ones become the big ones or if they're formed differently, which is pretty exciting.
Okay, we've got what I think is a very hard question from Jim now. Do we know what gravity actually is besides observing just what gravity does?
A question is, do we know what gravity is aside from observing what it does? I would say that observing what it does is like what science is. Physics is observing like what things do and how they behave and how they interact. And we do that with gravity. We can see how it affects stuff. We can do a lot of math to predict how it does stuff. So I would say we understand gravity quite well. It's funny in that we also don't know a ton about it on like trying to connect it to the other forces. If you want to talk about things like mathematical physics and even like parts of high energy particle physics, there's a lot of high-level conversations about trying to connect them because we can connect the 3 other forces, electromagnetic, which I guess is kind of 2, but it's 1. Electromagnetic, the strong nuclear force, and the weak force, which is like radiation stuff. We can connect all of those with math, but we cannot connect gravity to them. And if you think about it, gravity is like really easy to counteract on some level because like by raising my arms, like my arms are counteracting gravity right now and I can like jump and like counteract gravity. But also gravity is what keeps me on the Earth. And gravity is what keeps the moon around the Earth and the Earth around the sun and what keeps us in the galaxy. Like gravity is super, super strong over absolutely massive distances. So it's a funny force. But we understand it pretty well, I think. I understand it well enough to use it and appreciate it. Let's go with that.
Okay, I think we've got time for 2 more questions.
2 more questions.
So Ashley asks, any exciting new technology telescopes in the works?
Oh, so they asked about any exciting new technology telescopes in the works. So we are always coming up with new developments for new telescopes. A lot of you have probably seen news about the JWST telescope, which has recently been folded up for, I believe, the last time on Earth. And it's preparing for a launch at the end of October, which is super exciting. Me and a team of my colleagues have 2 proposals together that we are going to look at black holes, actually, with the James Webb Space Telescope. We're looking at the stuff in the disk a little bit further out and the stuff in this jet a little bit higher up than what you see right here. We can see that with the James Webb Space Telescope. So that is going to be super, super exciting for black holes. You can also see very, very distant black holes that are shining in the visible light, which will be cool. Other technologies. So for space telescopes especially, we have to prepare these like 15 to 20 years in advance of when they actually launch. Because developing technology for space is just very, very complicated and it's very, very dangerous. So there's a ton of testing that has to happen in advance. So I am on the steering committee for a telescope called StrobeX, which is proposed to NASA as a possible mid-budget class X-ray telescope that we could use to look at black holes eating stuff. That would be one of our prime science cases. It could also see like neutron stars exploding and like smashing together and stuff. It'd be very exciting. So with StrobeX, we are using a lot of technology that's already been developed. So we're using like NICER, the telescope on the space station that I showed. We're like kind of souping up parts of NICER to use. And we're also using parts of a previous instrument from the European Space Agency that was not ultimately funded. We're using that technology development as well. And these are detectors that were developed, I think, at CERN, silicon drift detectors. So we try to borrow from existing technologies as much as we can, so that way we're not testing out too many things all at once. But we have to prepare well in advance for these kinds of things. So if StrobeX were to go forward, it would launch in the, I think, mid-2030s or so. So we're always preparing in advance. There's also LINX coming up, we hope, as a Chandra successor to do imaging in the X-rays of like distant galaxies.
Okay, and the last question from Zach. With the gravitational lensing that you showed, is there a way to reconstruct the image of what is behind the star and actually use that to see very far away objects?
Yes. So Zach asks, with the gravitational lensing that we talked about at the very end, can we use technology and computers to reconstruct the image of what we were trying to take a picture of in the back and actually see really far away? Yes, exactly. We can use the black hole in the way, like a pair of glasses, to better see stuff that's further in the background that we wouldn't otherwise be able to see. Because when it gets lensed, it also gets like boosted a little bit, so it's a little bit brighter so we can see it better. So by having galaxies and like supermassive galaxies in the way of stuff, this can actually help us to see things further in the distance that we wouldn't otherwise be able to see as well. So when you look up things like gravitational lensing, there's various things like strong lensing and weak lensing, which are different techniques and technologies that we can use depending on how strong the effects are to see stuff that's further in the distance. And we can even use gravitational lensing to look for things like exoplanets around stars in our galaxy. Because the lensing, it's a very, very tiny effect when you're talking about a planet instead of a black hole. So they call it microlensing because it's a very small effect. But you can see a little bit of the star's light changing when there's a planet in the way. So gravitational lensing can be used to see more than just black holes also. Okay. I'm handing the mic back to Dan.
Okay. Thank you very much, Abby. That was a fantastic talk, and I learned a lot as well, and lots of discussion going on. So thank you very much for joining us for our last Great Lakes lecture of this season. So you can still follow us on GLL MSU on Facebook, and from there link to the Twitter and everything else. And we'll be back in the fall, but taking a break over the summer. I also wanted to take this opportunity to thank very much Paul and Terence from the MSU Library, who have set up this wonderful system we have here in the DSL room. And when people are able to come back to campus, this is going to be a great place to also have interactive sessions with schools and so forth, because you have a 360-degree setup. You're actually only seeing a part of the setup here behind, but they worked really hard to get the audio and the video and everything as good as you've seen it today for this fantastic talk. And also thank you to Elias Aidi for the social media and everything else that he's done as well. So thank you much everyone for joining. Have a nice evening. Thank you once again, Abby.
Very welcome. Thank you for joining, everybody.
And
we'll talk about black holes.
Yeah, and we'll speak to you soon. Thank you very much. Bye-bye.